Let us start. Hi again, welcome back. So today, let me remind you, we are going to start by showing two facts which I mentioned without proof in the previous lecture. There was the fact number 2, which is that the Permutohedron is the Minkowski sum of a bunch of line segments. And later, where such polytopes are called zonotopes, and later we're going to study these zonotopes a lot, but for now let me just write down, even do it like this: alpha over 2 in phi prime, where phi prime is the set of positive roots. Of type A. And the second fact, well, fact number 3 was that the Permutohedron is also the sum of all these hypersimplices plus the extra shift, which you can think of delta and comma n. Yeah, so, and then we had the pictures, right? The hexagon. For the fact number 1, the hexagon was the sum of these segments which make 120-degree angles, and then, or 60-degree angles, I guess. That's 2, and then for fact number 3, the same hexagon, although I'm drawing it differently, was the sum of 2 triangles. And then there was a lemma, right? I was trying to prove these facts using a certain useful lemma. And the lemma was that if you have a vector h in R to the n, then, or maybe R to the d, then for any two polytopes P and Q inside R to the d, the face of P plus Q, which maximizes the dot product with H, was the Minkowski sum of the two corresponding faces of P and Q. All right. Any questions so far? All right, no questions. Then I have a question. How do I prove of fact number 2? Any suggestions? Yeah? Wait, say it again. You know the vertices of Pn. Wait, that's for the hypersimplex, right? For Pn, it was permutations of 1, 2, 3, all the way up to n. Oh, okay. So you want to take the face of the Permutohedron corresponding to the H vector of the form 0, 0, 0, 1, 1, 1, 1, 1. Is that? Oh, okay. So that's actually, so if you want to take H 0, 0 all the way up to 0 and then 1, what is fh of phi sub n? Okay, interesting. Right, because if we just want to maximize the product with h, then the last coordinate should be maximal, and then the rest can be anything. So it's sort of finely isomorphic to the n-1 permutohedron. Okay, and what do I do next? Oh, you want to do induction, and you want to look at each of those, and then, yeah, you can. I think you can do induction. That could work. As usual with Permutohedra, you can do induction, and yeah, this could actually work. And any other suggestions which? Oh, you want to take H generic. And for example, let me even say if H1 is less than H2, etc., less than H sub n. Then what is FH of the Permutohedron? The entire thing. Okay, so it's either one vertex or the entire Permutohedron. Yeah, it's actually, I mean, if H is generic, then FH should be just a single vertex. If H was 0, then it would have been the whole thing. So it's a single vertex, and then you're saying it's the one corresponding to the identity permutation. 1, 2, all the way up to. Okay, and then what do I do with this information? Okay, let's find FH of the reference. If H is generic and satisfies this condition, then FH of the yeah, let's even try, because we have the lemma, right? So we can take just a single line segment here. What is FH of negative alpha over negative EI minus EJ over 2, comma, EI minus EJ over 2? Okay, so this is a line segment, so it has to be one of the endpoints. And then which one? Okay, it depends on which HI is bigger, whether HI is bigger than HJ. And so I and J have to satisfy, they're not just arbitrary, right? I is less than J. I is less than J, then hopefully this, EJ minus EI over 2. And now if you take the sum over all I less than J of EJ minus EI over 2, what do you get? We get what we, okay, so what's the maximal? Minus n plus 1 over minus n plus 1 over n plus minus n plus 3 over 2, then all the way up to n minus 1. Very nice. And then you have this extra guy here. And so as you add this extra vector to that vector, you get that FH on the right-hand side is what we need. And what do I do after that? Everything is symmetric. Okay, very nice. Yeah, that's That's the key tool that you can use whenever you have these symmetric polytopes. So Sn acts on both sides. So you can actually, if H has any other relative order of the coordinates, you see that the two vertices are going to coincide. I'm done with the proof. It's enough to figure out the vertices. It's enough to take H to be generic. All right. What about the other fact? Let's take H to be generic. Let's say we even take this same condition. Right? An example of a generic vector. Then, as we know, the FH of the Permutohedron is 1, 2, all the way up to n. What about the right-hand side? H of delta k comma n. Okay. So the vertices of this guy are basically any permutation of k ones and n minus k zeros. If you want to maximize the dot product, you take e n minus k plus 1 plus etc. plus e n. Is that right? Okay, and then you take the sum over all of these deltas, and h of the right-hand side is basically the sum of all such vectors plus the extra 1, 1, 1, 1, 1. So it seems like I'm going to get the same vertex, right? And then again, Sn acts on both sides. So we're done. Any questions on these proofs? All right. So today I want to actually try to explain some generalizations, because these facts are nice, beautiful, sort of unexpected facts. To what extent can you generalize them? And I think this is a nice opportunity for me to talk about something that's, I think, very important. So I'm going to explain root systems to you. And some of you probably already know root systems. By the way, how many people know about root systems? Definition: 1, 2, 3, 4, 5, 6. All right, about half of all people. That's perfect. So those of you who know, just try to think about how to generalize these two facts to root systems. If you don't know root systems, then I'm going to explain them. It's not going to take very long. So I'm going to start with reflection groups. And so basically, that's not some sort of coincidence. A lot of nice facts from combinatorics can be generalized to root systems. It's usually a very fruitful idea to ask, if you have some fact, well, how does it generalize to root systems? And in particular, to motivate the notion of a root system, let me first introduce reflection groups. So let's say you have some non-zero vector alpha. And then I'm going to denote by h sub alpha the set of all, it's basically its orthogonal complement. Alpha perp, it's the hyperplane of all vectors which have dot product 0 with alpha. And later we're going to study hyperplane arrangements like this. So, but for now, let me even introduce the notion of a reflection. A reflection S sub alpha is a linear map from R due to itself, which sends alpha to negative alpha and then preserves the hyperplane. Okay. So here's the question: what is if you have an arbitrary vector x, let's say its coordinates or whatever, what is the formula for the reflection of x with respect to this hyperplane? Picture is hyperplane. You have alpha, and then you have some vector x. Then you try to reflect. So while you're thinking, let me try to introduce some notation, which is going to be very convenient for root systems. So I'm going to denote for each alpha, for each non-zero vector alpha in R to the D, for alpha such that it's non-zero. Let me denote by alpha check the a vector that's proportional to alpha with this coefficient. Just whenever you have the longer, I want to find a vector proportional to alpha such that the dot product is equal to 2. That's my convention that I'm going to use next couple of lectures at least. All right, so any guess for, yeah? Like this? Yeah. Okay, and then you're saying S alpha of x is y minus c alpha, something like that, right? Okay, but how do I find the formula? What's this? Okay, I take the dot product of both parts with alpha, and then I can. Okay. Okay, it's 1 over. Is it like this? No, it should be. Okay. All right, it should be something like this, right? Okay. So what's the, and then y is, I guess, x minus this thing. Then you subtract. So what is the formula after all the simplifications? X minus 2c alpha. This is equal to x minus 2c alpha. And so 2c alpha, oh, okay, x minus, very nice, the dot product of alpha check with x times alpha. Okay, very nice. So please either memorize this or find a way to quickly figure this out, because it's very useful to remember these formulas and use them very quickly in your head. All right, so you have these reflections, so whatever, the formula is whatever. And then I can ask for I can look for groups which are generated by reflections. That's called a reflection group. A reflection group is a group. It's a subgroup of the group of isometries of R to the D, which is generated by the set S alpha, where alpha runs over some set of vectors. All right. So a natural question is, when is a reflection group finite? So you start with a bunch of hyperplanes like this, and then you apply reflections in all possible ways. And the question is, when do you get finitely many transformations? And when do you get infinitely many? It's a pretty natural question. How do you find all of these finite reflection groups? And can somebody give me an example of a finite reflection group? Yeah. Say again. The Dihedral groups. Yeah, I can barely hear you, but you're saying the Dihedral groups. Okay. Answer. Well, okay. An example is dihedral groups, which basically you take the plane and then you draw a bunch of, you draw a regular polygon, and you take the corresponding hyperplanes, which in this case are just lines. Basically, if this angle is rational, then you're going to get a finite reflection group. Otherwise, it's going to be a rational multiple of P. Yeah. So, and somehow these reflection groups, there is not too many of them. If you think about it, there's only a finite number of families you can come up with. And they are nicely classified by root systems. So let me try to introduce root systems, which are, so if you've never seen this before, then I should say that these are like one of the most important objects in mathematics. They just appear everywhere unexpectedly. They classify Lie groups and Lie algebras and cluster algebras and all kinds of stuff. And so it's cool to know about them because they may show up in whatever you're studying in your math career. So what is a root system? A root system is a finite set I of non-zero vectors such that the following axioms are true. And the first one is that for each vector, first of all, it's non-zero, and the intersection of P with the line through alpha only consists of alpha and negative alpha. So for each vector, you have the opposite vector as well, and these are the only two on that line. The second axiom is that for alpha, these elements of P are called roots. For each root, the corresponding reflection preserves the root system. And that's kind of the most important condition. The more vectors you take, the more reflections you get, so the more conditions you get. If you start with like a few vectors and then you start reflecting, you're going to get more and more vectors. and more reflections, kind of similarly to what happens for these reflection groups. And finally, if you have two vectors, so this condition is going to look slightly weird, but it's called the crystallographic condition. Condition is that the dot product of alpha, beta, and alpha check has to be an integer. Has to be an integer, and what does it mean? It means that picture should look like this. You have your vector alpha, and then here's your hyperplane H alpha, and then you take your vector beta and you reflect alpha of beta. So then what is this dot product here? This dot product is how many multiples of alpha we have to subtract to go from beta to its reflection. All right. So in the picture, it looks like alpha, another alpha, another alpha. Have some number of multiple copies of alpha, and that number has to be an integer. This is the dot product of beta and alpha check copies of alpha in this string. So for any two roots, you have to have this crystallographic condition. And that's it. That's the root system. And each of them, by the way, defines, as you may guess from this notation here, each of them defines a reflection group. So and it's called the while group. While group of phi, it's denoted W sub phi. It's just the group generated by all these reflections. Any questions so far? All right, so examples of root systems. And one example is, well, the most important one, is the root system of type a n-1. And what does this mean? This just means that your set of roots, by definition, is the set of all vectors of the form ei minus ej, where, so here the condition is going to be slightly different. I just has to be not equal to j. Okay. And so let's check that this is a root system. How do I check that this is a root system? Let's say alpha is of the form ei minus ej, where I not equal to j. First of all, what is alpha check? And let me remind you that alpha check was 2 over alpha. That's just alpha. Thank you. Okay, and what is then, let's say x is given by x1, x2, etc., all the way up to xn. What is s alpha of x? Alpha of x. Let me remind you that I just erased this from the same blackboard, but it's given by this formula here. So what is it going to be? Oh, very nice. Okay, let me actually draw this here. So I have x1, x2, all the way up to xi, and then xj, and then xn. So all of these coordinates are going to be the same, right? 1, then question mark, xn. Okay, so you want a picture where I have xi and xj, and then alpha is ei minus ej, which is, I guess, so you want alpha here. Then this is going to be h alpha. So the reflection is swapping the two coordinates, which you can also just you can write down this formula. This dot product is xi minus xj, and this is ei minus ej. So you can algebraically also find that what you get is you just xj, and you just permute each reflection as alpha, just permutes the two corresponding coordinates. And all right, so what is the, let's say, well, first of all, let's check the axioms. Is the first axiom true or false? True. Why is it true? Okay. We certainly have. Can you say it louder? All right. Oh, there is nothing. Oh, okay, so you're checking the second axiom, right? No, okay, but that's all right. So okay, the first axiom is easy indeed. Like each clearly, if ei minus ej is in my set, then ej minus ei is also in my set. So, and for the second axiom, this is the interesting one. So you wanna alpha is ei minus ej, and then beta is ea minus eb, and as alpha of beta is, it's not like sometimes there's nothing to permute, and sometimes there is something to permute, right? But so why does it belong to the root system, or does it sometimes not belong to the root system? All right, so you're saying that basically this is the set of all vectors where there's one coordinate is +1 and one coordinate is -1. And as you permute those, you get vectors of the same form. So yeah, it belongs to the root system. All right, so the second axiom is easy. And then what about the third one? Yeah? Okay, I see. So and well, there is also a sign, but up to a sign, it's just the size of intersection of the set ij and the set ab. So yeah, it's the third axiom is also true. So this is a root system. And by the way, what is the Weil group? What is the Weil group of a root system of type A n? Sn. Nice. Okay. So, and that's the most important idea. You have the symmetric group, and you have very nice things to say about the symmetric group. But now you have all these other root systems, or maybe there is no more root systems, but we're going to see some more examples. But then basically every statement you know for the symmetric group should generalize to arbitrary root systems in some beautiful way. And let me first convince you that there's at least some other root systems. So, and the nice examples to memorize are the ones when, well, actually, let me give you a complete, well, first of all, yeah, examples where the two-dimensional root systems. And basically, there is only 3 kinds. So the first one is type A2, which I already showed you here. So what is the root system of type A2? How does it look like? Yeah. Okay. So you wanted to. Yeah, let's do A1. A1 is you have the plane, and then you have this vector E1 minus E2, and then you have E2 minus E1. Type A1. And then what about A2? So this is sort of one-dimensional. The span of all roots is one-dimensional. And so for A2, the span is going to be, again, two-dimensional, right? Because the sum of all coordinates is 0. And how many vectors am I going to get? How many? 6. Okay, and how is it going to look like? Hmm? And etc. So there are 6 vectors. Okay, and how? But this should be a picture in the plane, right? And the coordinates are. Oh, nice. You get the whole. Okay, I see. So you're thinking about the generalization already. Okay, that's interesting, and that's actually that's not going to work, but it's still a nice idea. So indeed, if you add 2 to each of those, you get the Permutohedron. So the type A2 root system actually looks like vertices, the endpoints of the vectors form a regular hexagon. E1 minus E2, E2 minus E3, E1 minus E3, and then there 2, 1, and E3 minus E1. All right, that's A2. And then let me also show you B2 and G2, because it goes A, B, and then G. So for B, I need to draw a square and then draw my vectors like this. That's B2. And then for G2, also try G2. That's a little harder to draw, but I'm going to try. So I need to draw a pair of equilateral triangles like this. And then I just draw all these. There's going to be 12 vectors. Okay. And how do I check that these satisfy the axioms? Is it easy to check or is it hard? Do they even satisfy the axioms? I just erased the axioms, but the first one was that basically on each line there is exactly 2 roots, or 0 or 2 roots. That's true. And then what about the fact that S alpha of your root system is the root system again? Is it true or false? True. Okay. Right. If I take any alpha and then take the orthogonal line, then the reflection preserves the whole root system. And similarly here, there is the right angle between this vector and this vector, for example. So if I know it's probably hard to see, but if this is alpha, then S alpha reflects everything along this line, so it's preserved. If alpha is this vector, then everything is reflected along this line. Okay, I see. All right. Yeah. So you can take alpha to be this guy, and then you flip the whole picture. Yeah. Anyways, this union of two triangles, it has a symmetry and a six-fold symmetry, and it all works out. And then, well, okay. What about alpha, beta? Well, alpha check comma beta has to belong to Z. Is that true or is that false? What is the scaling? Well, the scaling is you take two exactly the same equilateral triangles. One is rotated along the center of mass. Yeah, that's actually a good question. So let's say I replace each alpha by C alpha, where C is bigger than 0. Then what is going to happen to alpha check? Then is going to be, okay, alpha check is this guy here. It's going to be, okay, so it's going to be decreased by C. And then I have this condition that alpha check comma beta is integer, and that happens if and only if alpha check over C beta is an integer. So it works. Yeah, we're going to consider them modulo, this scaling, and taking direct sums of two root systems is going to always give you a root system. So there are some simple operations. But yeah, anyways, it is true that if I rescale this picture, then the property of being a root system is not going to change. It's not going to depend on the scale of my picture. So anyways, let's see. So who thinks this is a root system? Okay, two people. Yeah, 3 people. Okay. I mean, basically, what do I have to check? I have to check all pairs of these vectors. And so let's say I try maybe some alpha and some beta. I know, maybe this is alpha and this is beta. Where is S alpha of beta? What is less than alpha? This one or no? Which one? Yes, this one. Oh, okay. You have to reflect as alpha reflects with respect to the hyperplane orthogonal to alpha. Okay, so then this guy is S alpha of beta, and then I have to look at the vector. How many multiples of alpha do I subtract from beta to get S alpha of beta? And the answer is 1. The geometry of this picture is such that there is alpha, and then there's a short beta. And this is S alpha of beta, and then this is negative alpha. All right. Well, and then you can keep playing this game. So maybe I take this guy to be beta, and then S alpha of beta is going to be this guy here, and this is again going to be alpha. And then I can keep going. I can take any 2 vectors, so it's a nice exercise for you to check. So this is a root system. And the claim is that there is no more. Well, there is, strictly speaking, there is something called A1 union. Just take the 2 orthogonal copies of A1, which is going to give you a picture like this. That's also a root system where the span of the roots has dimension 2, but there is no more. And this, I'm going to call this not irreducible. These are irreducible, but this can be decomposed into direct product, direct sum of 2. So this is not, this is reducible. And I'm going to ignore such root systems. So there is okay, but these are all right. So let me say this precisely. I'm going to call a root system reducible if it can be decomposed into a disjoint union of 2 root systems such that any 2 vectors, alpha 1 and alpha 2, are orthogonal. Alpha 1 in phi1 and alpha 2 in phi2. Right? So in this, in type B, you're saying that I can take these 4 vectors and then the other 4 vectors, but this condition here is not true. Not an orthogonal direct sum of 2 root systems. All right. And so it turns out that there is, you have the axioms, and then you have this irreducibility, and modulo those conditions, there is only a finite list of root. Oops, I have 3 minutes. Okay, let me tell you all root systems. Complete list of all root systems in 3 minutes. First one is an minus 1, which has the definition over there. And the next one is bn, which consists of all vectors plus or minus ei, I in bracket n, disjoint union plus or minus ei, plus or minus ej, where I is less than j. And for n equals to 2, you get this times p2 here. The next one is cn, which is the same as here, but you take plus or minus twice ei disjoint union plus minus ei plus minus ej. And then the next one is dn, and it consists of just plus or minus ei plus or minus ej. And then there's also E6, E7, E8, and F4, and G2. So the index here is the dimension of the span of my root system. So whenever you see E6 means that the span of all roots is 6-dimensional. And I'm not telling you what these are, but what I am telling you is that this is a complete list. There is no more. There is 4 nice infinite families. And then there is like 5 exceptions. One of them looks like this. There is no higher dimensional version of G2, but there is a higher dimensional version of B2 for any Bn for any n. And it's a nice exercise for you to take home to check that all of these are root systems and to go to Wikipedia and read the coordinates of all roots of all these root systems. But basically, if you want to like type B corresponds to like symplectic group and type D to the orthogonal group or whatever. I don't even remember. Type A corresponds to the special linear group. These corresponds to different Lie groups, which by definition are just groups that are also smooth manifolds. Like it's crazy that this simple description actually shows up in so many places. And each of them is a cluster algebra, etc. So anyways, I'm out of time, and we're going to continue next time. And we're going to define a Permutohedron for each of them and try to generalize our facts about Permutohedra for each of those roots.